Okay, we have a quantum mechanics semester 2 practice final exam. Let's begin. So number one, a particle is confined in a one-dimensional infinite square well, where we have here the V of x is the potential energy. We have this piecewise function, 0, comma, domain 0 is less than x is less than a, comma, uh, infinity, comma, otherwise. And we have a perturbation is added, h prime equals lambda v naught x over a, where lambda is much less than 1. Okay, so let's begin with letter A. Find the first order correction to the ground state energy. All right, so time-independent perturbation theory problem. Okay, infinite well, and from 0 is less than x is less than a. We have first unperturbed eigenstates. Okay, so we have that psi sub n of x equals square root of 2 over a times the sine of n pi x over a. We have the unperturbed energies, okay, right here, set equal n squared, pi squared, h bar squared over 2m a squared. Perturbation, h prime, that's equal to lambda v naught x over a. So here we have our first order correction. Here's our first order correction. Okay. So here, this is our integral that we're going to set up from the first order correction. Okay. And this e sub n superscript 1, okay, that's going to come up here. When we integrate, this is our setup. We're going to have lambda v naught 1 over a times 2 over a, 0 to a. The integral is going to be x, and then here we have that modulus there squared of that psi n of x. So that's going to become sine squared n pi x over a, integrating there dx. Okay, for any n from 0 to a, x sine squared of n pi x over a dx, that's going to come out to a squared over 4. Okay, so our first order correction here is going to come out to lambda v naught 2 over a squared times a to the 4th. Okay, so our E sub n superscript 1, first order correction of the ground state energy, comes out to lambda v naught over 2. Okay, so after that integration, that comes out. And I'll try to, by the way, I'll try to go through this quickly. Some of the computation, algebra, trig, behind the calculus, I'm going to go through quickly where I won't show some of the steps. I assume, you're good with it. So letter B, moving along, find the first order correction to the first excited state energy. So the first order correction to the first excited state energy, right here, we have that E sub 1 superscript 1. We know that's going to be equal to lambda v naught over 2. And then E sub 2 superscript 1, that's going to equal to lambda v naught over 2. So that's all we have to do for letter B. Letter C, determine whether the perturbation increases or decreases the energy spacing between the first two levels. Okay, so letter C is here. So we have the first two levels, they shift by the same amount. So the spacing is unchanged to the first order. So spacing is unchanged for that delta E. Subscript 2, 1, superscript 1, that equals 0. We're good with that. That's letter C. And now letter D. Explain physically why parity arguments do or do not simplify this problem. Okay, so what we could say here for letter D, parity does not simplify the problem much because the well is from 0 to a. It's not centered at the origin. If the well were centered at x equals 0, parity would be more directly useful. Okay, so that takes care of A, B, C, D for number 1. And that being said, we can now move on to number 2, Hamiltonian, that we're going to be given here. Okay, number 2. Okay, consider the Hamiltonian. H equals p squared over 2m plus alpha times absolute value of x, where alpha is greater than 0. We're going to use the normalized trial wave function psi of x equals ae negative beta x squared. So part A, they want us to normalize the trial wave function. So this is in regards to the variational principle, and our Hamiltonian is given to us here. Our trial wave function given to us here. So in order to normalize that, what we need to do is we need to integrate from negative infinity to infinity. That modulus of psi of x, that's going to be squared. Integrating that, normalizing it, we want to set it equal to 1 because we want to get our a, we're going to want to get our a squared value. So that being said, we're going to have an a squared on the outside of the integral from negative infinity to infinity, e to the negative 2 beta x squared dx, that's equal to 1. So integrating here, this comes out to square root of pi over a. So that's our integral. So we're going to get a squared times the quantity square root of pi over 2 beta, that equals 1. Take the square root, we're going to take the positive square root of that, so that's going to be the 4th root of 2b over pi, or quantity 2b over pi raised to the 1/4. So that is our a value. We've normalized the trial wave function for part B. Okay, so we have the, we want to compute the expectation value of the kinetic energy. So right here for part B, we have the expectation value of T, so, or average kinetic energy. That's going to be equal to negative infinity to infinity, psi asterisk quantity times the quantity, negative h bar squared over 2m times d squared, and times this d squared over dx. That's, we have a derivative here, right? This d squared over dx squared times the psi dx. So here, second derivative, right? So 4 equals 4 rather, psi equals ae to negative beta x squared. We have that. Take that second derivative of psi with respect to x, that equals, when we do the derivation, after the first, we get the second, it's going to be a times the quantity 4 beta squared x squared minus 2 beta times e raised to the negative beta x squared. Okay, so there, for our expectation value of t, that's going to come out to, on the outside of the integral, we have a negative h bar squared over 2m, integrating from, integrating psi times the quantity 4 beta squared x squared minus 2 beta psi dx. So what's going to happen there is we're going to get that expectation value of t equals negative h bar squared over 2m quantity, okay? And then we have that 4 beta squared x squared negative 2 beta, right? So here, for this normalized Gaussian, okay, for this expectation value of x squared, that's going to equal 1 over 4 beta, right? And so the expectation value of t, that's going to be negative h bar squared over 2m, quantity beta minus 2 beta. And what's going to happen here is our expectation value of t in this situation is just going to be h bar squared beta over 2m. So normalized Gaussian, and this is what we get here. That's for letter B, the kinetic energy's expectation value. Letter C, we want to compute the potential energy. Okay, so we're going to start out here computing the potential, for letter C, compute the expectation value of the potential energy. My apologies. So here, expectation value of the potential energy equals alpha of the expectation value of absolute value or modulus x. So we have expectation value of modulus x. That's going to equal a squared integrated from negative a squared times the integral from negative infinity to infinity. Absolute value of x times e to the negative beta, times e to the negative 2 beta x squared dx. So we're going to integrate this. Okay, now here's a good thing. We have an even integrand. So because the integrand is even, that expectation value is going to be equal to 2a squared. Change the limits from 0 to infinity now, times x e negative 2 beta x squared dx. So here's our new integral we're dealing with. And then we're going to move on to our integration portion of this. Okay, so what we're going to do here in this situation is we're going to use that integral from 0 to infinity x e to the negative kx squared dx. When we integrate that from 0 to infinity, we get 1 over 2k. Now with k equals 2 beta, we're going to integrate from 0 to infinity x e to the negative 2bx squared dx. When we integrate that, that's going to come out to 1 over 4 beta. So therefore here the expectation value of modulus x, that's equal to 2a squared times 1 over 4b. We're going to get a squared over 2 beta, beta, 1 over 4 beta. We get a squared over 2 beta. Now what's going to happen is, this is going to have our situation a squared equals square root of 2 beta over pi. Then our modulus here, our expectation value of our modulus of x, that equals 1 over 2 beta times the square root of 2b over pi. And from there, what we have is expectation value of the modulus of x equals 1 over the square root of 2 pi beta. Okay, from here to here. So in regards to that potential energy, because that's what we were computing the expectation value of, the V, our potential energy's expectation value is going to be alpha over square root of 2 pi beta. Okay, and from the previous page, part D, we want to find the variational estimate of the ground state energy, okay, for part D. So for the variational energy, okay, so we have that E of beta. That's going to be just the sum of the expectation value of T plus the the potential energy's expectation value. So taking those sums and substituting, we get that variational energy is going to be equal to h bar squared beta over 2m plus alpha over square root of 2 pi beta. That takes care of letter D. And for letter E, we want to determine the optimal value of B. So we want to, the optimal value of beta. So we want to optimize this beta. So what we do is we're going to take the derivative dE with respect, the derivative of E with respect to beta, that equals 0. Set it equal to 0 because we're looking for optimization. So that derivative, dE dB, equals h bar squared over 2m minus 1/2 times alpha over square root of 2 pi beta to the negative 3/2. Set that equal to 0. And we want to solve for beta, right? So just performing the computation here, all right? We're going to get the optimization there of beta. That's going to equal m times alpha in the numerator over h bar squared times square root of 2 pi in the denominator. All of that quantity raised to the 2/3 power, and that would be the optimal value of beta. So that takes care of A, B, C, D E for number 2. We can move along now to number 3. Okay. So, number 3, we have a particle of mass m encounters the potential barrier. So we have V of x equals V naught, quantity 1 minus x over L, from 0 is less than x is less than L, and 0 otherwise, where E is less than V naught. For part A, determine the classical turning point. So for this, okay, we have WKB, potential barrier is given. With this condition here, so our turning point, the turning point is going to satisfy E equals V of x sub t. And E equals V naught 1 minus x sub t over L. So E over V naught, that equals 1 minus x sub t over L. So x sub t equals the quantity L times, x sub t equals L times the quantity 1 minus E over V naught. So that takes care of our turning point for letter A. Moving to letter B, using the WKB approximation, derive an expression for the transmission probability. So, part B, WKB tunneling probability. We acknowledge that the classically forbidden region is going to be from 0 is less than x is less than x sub t. So, the WKB transmission factor is approximately t. T is approximately e to the negative 2y, where our gamma equals 0. I'm sorry, that's gamma. Sorry about that. Sometimes I pronounce y as gamma from just looking at it too fast. T is approximately e to the negative 2 gamma, where gamma equals 0 to h sub t kappa of x dx. So isolating this, integrating, we're going to get k of x by itself equals numerator square root of 2m quantity times the quantity v of x minus e divided by h bar. Okay? So that's your k of x, all right? But what we want to do now, right, after we find that k of x, we want to integrate, we have this gamma, right? So here's what we need to do for this. Let me just get this more in focus, sorry. Okay, so we have gamma equals square root of 2m over h bar. We're integrating from 0 to x sub t. Quantity square root of v sub naught times 1 minus x over L, and then minus e. So u substitution, we're going to let u equal v naught, quantity 1 minus 8 x of L minus e, everything inside the radical. Then du is going to be negative v naught over L dx. dx is negative L over v naught du. So at x equals 0, u equals v naught minus e, and at x equals x sub t, u equals 0. Okay, so we've changed of variables here. So gamma equals square root of 2m over h bar times L over v naught. We're integrating now from 0 to v naught minus e, and inside becomes u to the 1/2 du. Okay, so we can integrate that. Okay, gamma equals square root of 2m over h bar L over v naught. Integrating this becomes 2/3 u to the 3/2 from 0 to v naught minus e. So our gamma is equal to 2L now. Once we substitute our limits of integration, gamma is equal to 2L times square root of 2m over, that's a 3h bar v naught. So that's 3h bar v naught times the quantity v naught minus e to the 3/2. So we have our t, or tau, approximately the exponential of this whole quantity, negative 4L square root of 2m over 3h bar v naught times quantity v naught minus e to the 3/2. So this would be our expression for the transmission probability. Okay? So let's see what we have here. Moving along into letter C. Letter C, from the previous page, explain qualitatively how the tunneling probability changes as L increases. So what we could say here is the effect of increasing L, the exponent is proportional to L. So as L increases, RT decreases exponentially, or R tau, or RT rather. A wider barrier makes tunneling much less likely. Okay. Pardon me if I misspoke there for a moment. Part D, because I'm just trying to get you through this quickly, because you could always pause things and go back and forth. Part D, under what physical conditions is the WKB approximation valid? Well, for Part D, the validity of the WKB is valid when the potential changes slowly over 1 de Broglie wavelength. And here we have the qualitatively written expression, and equivalently, we have the other expression written under it, those respective modulus here and modulus here. And those are away from the turning points. Okay, so that's letter D. And now we could, I believe that's 3, A, B, C, D. Yep, we can move along to number 4. Okay, so moving along to number 4, time-dependent perturbation theory. Let me just get this in focus for number 4. Yeah, that's good enough for now, because then we'll just shift it to here. A 2. So for number 4, a 2-level system has unperturbed states. We have that Ket 1 and Ket 2, right? Ket 1 and Ket 2 with energies E sub 1 and E sub 2, and a time-dependent perturbation is applied. H prime of t equals V naught cosine of omega times t. And then we have our matrix element here. Our matrix element between the states is Bra2 H prime Ket 1. Okay, that equals V. And part A, using the first order time-dependent perturbation theory, derive the transition amplitude from Ket 1 to Ket 2. So here's what we can do for part A. Time-dependent perturbation theory, we have 2 states, Ket 1, Ket 2. Energy difference, right? So we have that energy difference in this situation. We're given as E sub 2 minus E sub 1. And here's our perturbation matrix element. That equals V cosine of omega times t. So our transition amplitude, so our transmission amplitude, we're going from 1 to 2, right? Okay, so since we're going from 1 to 2 here, first order transition amplitude, that's going to be that of t, negative I over h bar 0 to t, right? And then we have our 2 bra h prime of t prime bra Ket 1 Ket e to the negative I w sub 2 1 t prime dt prime. This is our first order transition amplitude. Okay, so moving down here, what this becomes is negative I times V over H bar, 0 to t, cosine of Wt prime, e to the I W sub 2, 1, t prime, dt prime. Okay, now what we're going to do here is we're going to split this up, use cosine of Wt prime, that's going to equal 1/2 e to the I keep saying W, my apologies, omega. E, I do that all the time. Sorry about that. E-I omega t prime plus e to the negative I omega t prime. My apologies. Okay, then we have this transition amplitude. It's going to be IV over 2 h bar. We're integrating from 0 to t. E to the I, W sub 2 1 plus W times t prime plus E to the I, W sub 2 1 minus, again, W, omega sub 2 1 minus omega, close parentheses, T prime, times dt prime. Didn't have enough coffee this morning, my apologies. Integrate. So when we integrate here, all of this from 0 to t, I'm just going to leave it here because it's here. I'm not going to try to say it because I don't want to, bumble the expression. There it is. Okay. So, letter A, here is our first order time-dependent transition. Here's our transition amplitude from ket 1 to ket 2. Or 1 ket 2 ket 1 to ket 2. There you go right there. All right. And that's after performing the integration. That's after performing all of that integration. Part B, find the transition probability. Well, let's see what we could do. I'm just going to adjust this. There we go. So, exact first order probability, we're going from 1 to 2. Okay, that's going to be this modulus squared. Okay, so near resonance, the second term dominates because your omega is approximately omega sub 2 to 1, 1 to 2, 2 to 1. I'm just gonna read it as W sub 2 1, just for brevity's sake. So let your change equal W sub 2 1 minus W. Again, I shouldn't say W, but it's easier to say W than omega, but that is omega. Omega sub 2 1 minus omega. Then we have our transition here, probability. We're trying to get this C sub 2 superscript 1 of t. That's approximately V over 2 H bar times e to the I delta t minus 1 over delta. Okay? So we're going to take that modulus of that term here. So that modulus of e to the I delta t minus 1 squared, that's going to become 4 sine squared of delta t over 2. So what we're going to get here in this situation is this. Okay, so that probability, 1 to 2, that transition probability is approximately modulus of v squared over h bar squared times sine squared of change in t over 2 over delta squared. So we have an exact resonance at delta equals 0. And the limiting form is going to be this. The transition probability in this case is going to be approximately the modulus of v squared times t squared over 4h bar squared. So that would be the transition probability. That's part B. Moving along to part C and D. So for part C, we want to show that the resonance occurs when h bar omega equals the difference between e sub 2 and e sub 1. So the resonance condition, resonance occurs when our omega is approximately omega sub 2 1. So since omega sub 2 1, e sub 2 minus e sub 1 in the numerator over h bar, the resonance condition is h bar omega is approximately e sub 2 minus e sub 1. Okay, so part D, explain physically why resonance enhances transitions. So the physical explanation here is the external perturbation supplies energy packets of size approximately h bar omega, that product of h bar and omega. When this matches the level spacing, the system absorbs energy efficiently, producing a large transition probability. Okay, so that takes care of number 4, and now we're going to move on to number 5, Fermi's golden rule. Okay, so number 5, Fermi's golden rule. So an atom initially in the initial state interacts with a weak oscillating perturbation and may transition into a continuum of final states. Okay, so this is ket I, initial quantum state. Part A, starting from time-dependent perturbation theory, state Fermi's golden rule. So this is a textbook type question, notes. Part A, Fermi's golden rule gives the transition rate from an initial state, ket I, initial quantum state, to a continuum of final states. Okay, so here is the formula we have for Fermi's golden rule. Okay, where energy conservation requires the following: E sub F is approximately E sub I, the final is approximate to the initial, or for an oscillating perturbation, E sub F is equal to E sub I plus or minus H bar omega. So this is more of a textbook type problem, well, portion of it. So let's move on to B. Explain the meaning of the density of the states factor. Okay, so for part B, the density of states, rho of E or G of E, it tells how many available final states exist per unit energy near E. A larger density of final states means more possible transitions, so the decay or transition rate increases. So that takes care of letter B. Letter C, suppose the perturbation matrix element is constant, and we get this H prime sub Fi modulus of that equals H naught. If the density of states is G of E equals C e to the 1/2, derive the energy dependence of the transition rate. Okay, so for part C, here's what we can do. Okay, so we want energy dependence, again, of the transition rate. Here's what we were given, and we're going to integrate here. I'm sorry, we're going to take, for our energy dependence of the transition rate, that's going to be equal to 2 pi over H bar times modulus H sub naught squared times G of E. Now, this is going to be 2 pi over H bar, H naught squared times C e to the 1/2, because we're just substituting here. So this is going to be proportional to e to the 1/2. So in this situation, the energy dependence of the transition rate equals 2 pi C H naught squared over H bar times e to the 1/2. So that's our energy dependence of the transition rate. Part D, they want us to explain qualitatively why excited atomic states decay spontaneously. Okay, so for part D, excited atomic states are not perfectly stable because atoms interact with the electromagnetic field. Even in vacuum, the quantized electromagnetic field has vacuum fluctuations. These allow the atom to emit a photon and transition to a lower energy state. So spontaneous emission occurs because the excited atom can lower its energy by radiating electromagnetic energy. Okay, so that takes care of Fermi's golden rule problem A, B, C, and D. And let's move along to number 6. Okay, so moving along, number 6. Alrighty. So, part number 6. 2 identical spin 1/2 fermions occupy a one-dimensional harmonic oscillator. So, part A, construct a properly anti-symmetric spatial spin wave function for the ground state. Okay, so here's what we could do here. Identical particles and helium situation. Single particle energies, that's E sub n equals H bar omega times the quantity n plus 1/2, with n equals 1, 2, on and on and on and on and on, positive integers. A, what we could say here is the ground state antisymmetric wave function. Both fermions can occupy the spatial ground state only if their spins form an antisymmetric singlet. And here's our spatial part. That's psi naught of x of 1 times psi naught of x of 2. This is symmetric under that exchange. 1 to 2, 2 to 1. Therefore, the spin of that must be antisymmetric. So we have this singlet. What we're going to have here is 1 over square root of 2, right? And then we have the up-down spin minus the down-up spin, or spin up, spin down minus spin down, spin up, okay? Thus, the total wave function is going to be the following. Total wave function is going to be psi naught times x of 1, psi naught x of 2, times 1 over root 2, and then times our spins, difference. The difference between spin up, spin down, and then minus spin down, spin up. So, this is our total wave function of the ground, for the ground state. For part B, explain why two fermions cannot occupy the same quantum state. So this is based on the Pauli exclusion principle. Fermions require the total wave function to be asymmetric under this exchange, right? Psi of 1 of 2, that's going to equal that negative psi 2, 1. So if two fermions had exactly the same quantum state, the anti-symmetrized wave function would vanish. So this, okay, is going to become 0. And we could say, therefore, two identical fermions cannot occupy the same complete quantum state. Okay? So that takes care of number 2, letter B. Moving along, letter C. And letter C, we want to determine the ground state energy of the system. So ground state energy, what we could say is both particles occupy n equals 0 with opposite spins. Each has energy E naught equals 1/2 h bar omega. Total, our E subground, our ground state is h bar times omega. That's our ground state energy of the system. Moving along to part D. Now consider the first excited configuration. List all allowed total spin states. Okay, so let's see here for D. First excited configuration and spin states. The first excited configuration has one particle n equals 0 and one in n equals 1. The two spatial combinations are the symmetric and the asymmetric states. Okay. My apologies. These should be next to each other. Ignore that, the blue ink. So, two symmetric and antisymmetric. And for the fermions, the symmetric spatial part pairs with the antisymmetric spin singlet. And the antisymmetric spatial part pairs with the symmetric spin triplet, which are right here. Here's the singlet, here's the singlet, and here's the triplet. So, and the triplet spin states are as follows. You get up, up, and then 1 over that root 2, spin up, spin down, plus spin down, spin up, and then down, down for the triplet spin states. So that is part D. Part E, explain why the triplet helium state has lower Coulomb repulsion than the singlet state. So here's part E for the triplet state. The spin wave function is symmetric, so the spatial wave function must be antisymmetric. An antisymmetric spatial wave function tends to keep the two electrons farther apart because it vanishes when the electron positions coincide. Psi sub A of x comma x equals 0. That lowers the average Coulomb repulsion between electrons. Therefore, triplet helium states often lie lower in energy than corresponding singlet states. And pardon me if I'm speaking too fast, just trying to get you through it. And let's move forward to number 7. That takes care of 6. Okay, number 7. All right, scattering theory problem. So number 7, a particle scatters from the spherically symmetric potential. V of r equals V naught times e to the negative r squared over a squared. Part A, write the first Born approximation formula for the scattering amplitude. So scattering theory, here's our potential given. Part A, the first Born approximation for the scattering amplitude is going to be f of theta equals negative 2m over 4 pi h bar squared. And then we're integrating e to the negative iq dot r times v of r, and then that d3 r. So, d cubed r, where q equals k sub f minus k sub I. And q is going to equal modulus of q equals 2k sine of that half angle theta over 2. Now, for this Gaussian potential, f of theta equals negative m over 2 pi h bar squared times v naught times the integral here. That integral of e to the negative iq dot r times e to the negative r squared over a squared, d to the third r. Now, in this situation, the Fourier transformation, the Fourier transform of a Gaussian is the following. We have the integral of e to the negative iq dot r times e to the negative r squared over a squared, d to the third r. And that's going to equal, when we integrate that, that's going to equal pi to the 3/2 a cubed e to the negative q squared a squared over 4. And from that, we can find that f of theta equals negative mv naught times square root of pi a cubed over 2 h bar squared times the quantity e to the negative q squared a squared over 4, with q equaling right over here that 2k sine of 2k sine of theta over 2. Okay. Part B, determine the qualitative dependence of scattering on the parameter A. So down here's part B. The parameter A controls the region of the potential. The larger A means wider, longer potential. The larger A means wider, longer range potential. Okay, that's right here. A smaller A means narrower, shorter range potential. The amplitude contains a cubed e to negative q squared a squared over 4. At small scattering angles, q is small, so large A increases the scattering amplitude. At larger angles, the exponential suppresses scattering more strongly when A is large. So a wider Gaussian potential gives more forward peaked scattering. Okay, so that takes care of letter B. And now let's go to letter C and D, E. That's on the next page. Okay, so. Okay. All right. Letter C. So what do they want for letter C? Explain physically why low energy scattering is dominated by low partial waves. Okay, so at low energy, the wavelength is large. Okay, lambda equals 2 pi over k. Large wavelengths cannot resolve fine angular structure. Higher partial waves have larger angular momentum and are suppressed by the centrifugal barrier. Thus, low energy scattering is usually dominated by the S wave. So we get L equals 0, and sometimes the P wave, L equals 1. Okay, so that's for part C. For part D, what condition determines whether the Born approximation is valid. So here, the Born approximation is valid when the potential is weak enough that the incident wave is only slightly distorted. So qualitatively, this potential, the magnitude or modulus of the potential has to be much less than the energy, right? Than E. Or more generally, when the scattering amplitude is small and multiple scattering effects can be ignored. For this potential, here's our rough condition, M times that modulus V naught A squared over H bar squared. Okay, so is much less than 1. So this quantity much less than 1, and qualitatively that modulus of V has to be much less than E. And then for part E, we want to describe the physical significance. Describe the physical significance in this situation of the differential cross sections. Okay. And my apologies if I misspoke here. I think I misspoke here. There's the, can't remember what I just said, but here's what we have for the qualitative portion. Again, I didn't have much coffee. I hope I didn't misspeak here. Okay. Now, so part D, the differential cross section is, and I think I did misspeak there. Just follow the follow the mathematics. This is correct. Sorry, I'm a bit scatterbrained today, but this is correct. This is the correct answer. So if I misspoke, my fault, my apologies. Correct answer is on the paper. Letter E, the differential cross section is here. The d sigma over d omega, that equals that modulus of f of, f of theta squared. Okay? So, that being said, it gives the probability per unit solid angle that a particle scatters into direction theta. Okay? And for the Gaussian potential here, okay, d sigma over that d omega, that equals m squared v naught squared pi a to the 6 over 4 h bar to the 4th times that e to the negative q squared a squared over 2. Okay, so, all right, so that takes care of number 7, and again, my apologies for misspeaking on letter D. Okay, number 8. We're ready for number 8. Okay, number 8. Consider. Okay, so for number 8, we want to consider a relativistic electron described by the Dirac equation in a central Coulomb potential. Part A, explain why the Dirac equation naturally predicts electron spin. Okay, so for part A, we could say the Schrodinger, referring to the Schrodinger equation, is first order in time but second order in space. Dirac wanted a relativistic equation that was first order in both time and space. So that I, h bar, and then derivative of psi with respect to t equals c times alpha dotted with p plus beta mc squared, close parentheses, times psi. And that's our Dirac Hamiltonian. And we could say the matrices alpha and beta require the wave function psi to have multiple components. And for spin 1/2 or 1/2 particles, however you want to pronounce them, the Dirac spinner has 4 components. The spin degree of freedom naturally appears from the matrix structure of the equation. So, electron spin is not added artificially. It emerges from requiring compatibility between quantum mechanics and special relativity. So that is letter A. Moving along to letter B. Describe the physical origin of spin orbit coupling. Okay, so letter B here. In the electron's rest frame, the proton appears to move around the electron, producing a magnetic field. The electron's spin magnetic moment interacts with this magnetic field. This interaction produces an energy term proportional to L dot S. So the spin-orbit interaction has the form H sub SO is proportional to the dot product of L and S. So physically, it couples the electron's orbital angular momentum to its spin angular momentum. Okay, so that is part B. Moving along to part C. Part C, I'm just going to, let's just read it first. Using qualitative arguments, explain why relativistic corrections split hydrogen energy levels. Okay, so for part C, this is an interesting one. Okay, for part C. So, non-relativistic hydrogen energy levels depend only on n. And E sub n equals negative 13.6 eV over n squared. Relativistic corrections introduce dependence on additional quantum numbers, especially total angular momentum, J equals L plus S. Okay, so here, main corrections are relativistic correction to kinetic energy, spin-orbit coupling, and Darwin term. And together these produce fine structure splitting. Thus, states with same n but different angular momentum structure can have slightly different energies. And just a note here, relativistic hydrogen energy levels depend mainly on N and J. Okay, for part D, they want us to explain the significance of negative energy solutions in the Dirac equation. So the Dirac equation predicts solutions with energies E equals plus or minus square root of P squared C squared plus M squared C to the fourth. The negative energy solutions were historically puzzling. They led Dirac to propose the existence of antiparticles. So this is textbook stuff for letter D. In modern quantum field theory, negative energy solutions are reinterpreted as positive energy antiparticles moving forward in time. For the electron, the corresponding antiparticle is the positron. So actually most of number 8 is textbook stuff, textbook notes. And now letter E. Letter E, they want us, they're asking for letter E, what experimental evidence supports the existence of antimatter? Interesting stuff. Letter E, the positron was discovered experimentally by Carl Anderson in cloud chamber tracks. And a positron has the same mass as the electron, opposite charge, and behavior consistent with the Dirac prediction. Thus, positron discovery provided strong experimental support for antimatter and for the physical meaning of the Dirac equation. Very famous equation, very nice, elegant equation in physics. And that's all for this practice final exam for Quantum Mechanics 2. Hopefully this gives you some extra material to study with, and thank you for watching, and have a great day.